Hi everyone, thank you for joining us. We are Group 4 Cyphercraft, and today we will talk about the paper Zen and the Art of Virtualization. To start, let me explain the context behind this work. Around the early 2000s, servers were becoming more powerful, with lots of unused resources sitting idle. That created interest in virtualization, meaning the idea of running several virtual machines on one physical server. The problem was that existing solutions were far from perfect. Some virtualization systems were slow, others required special hardware, and some only worked with modified operating systems. In many cases, performance dropped a lot when several operating systems ran at the same time. There was also a lack of strong resource isolation, so one virtual machine could affect the performance of another. The authors wanted something better. They set out to create a virtual machine monitor that would run many operating systems efficiently, safely, with strong control over resources, and without a noticeable performance cost. That's how Zen was born. Zen is a hypervisor, or software that manages virtual machines, abbreviated to VMs. Hypervisors allow virtualization to be lightweight, independent of specific hardware, and efficient on resources. Hypervisors originally come in two types. Bare metal hypervisors are installed directly on the host hardware, while hosted hypervisors are run like programs through the operating system. Nowadays, most hypervisors like Zen take on properties of both bare metal and hosted.
Thanks, Isabel. The motivation behind Zen was simple. Build virtualization that feels almost as fast as bare metal, but still provides isolation and flexibility. The authors had four priorities. First, keep compatibility with existing applications so users do not need to rewrite software. Second, allow full operating systems, not just single processes. Third, aim for high performance. And finally, expose enough hardware detail to avoid unnecessary overhead. The interesting part is how they achieve this. Instead of fully emulating hardware, they use something called para-virtualization. This means that guest operating system knows it is running on a virtualized environment and communicates directly with the hypervisor using controlled interfaces. This reduces traps, avoids expensive instruction rewriting, and cuts down overhead. Zen splits responsibilities cleanly. The hypervisor runs at the highest level and schedules CPU and memory. Guest operating systems run just below it, slightly modified to avoid privileged instructions. As a result, Zen can host many operating systems at once, like Linux and Windows XP, while keeping performance surprisingly close to native speed.
Thank you, Jose. Let me walk through how Zen is structured and how the authors discover in their experiments. Zen sits directly above the hardware and exposes virtual CPUs, memory, and I/O devices. Each operating system runs inside a domain. One special domain, called Domain 0, has control privileges, such as creating or destroying other virtual machines, and allocating resources. Memory is handled carefully to avoid confusion between domains. Zen checks and validates updates to page tables to maintain safety. I/O uses shared memory rings, which lets data move efficiently instead of copying it again and again. In the paper, this technique allocates a very fast network and these operations. Now, for the results. Performance tests were impressive. Zen ran Linux workloads with only a tiny performance drop, often just a few percent. In many benchmarks, it outperformed VMware and user mode Linux. One of the strongest conclusions is that dozens of virtual machines can run together with predictable isolation. Each VM's performance stays stable even when others are heavily loaded. That is a strong achievement, especially for the time.
Thanks, Maria. Zen became an important milestone in virtualization research and had a big influence on how modern cloud platforms were built. One of the key ideas in the paper was paravirtualization, where the guest operating system is aware that it is running on a virtual machine. This avoided the heavy cost of full hardware emulation and allowed Zen to achieve much better performance. This idea later influenced real-world systems. For example, early versions of Amazon EC2 were built on top of Zen, showing that the concepts from this research could scale beyond the lab and into large commercial cloud environments. Even though this paper is more than 20 years old, many of the challenges it raises are still relevant today. For instance, as cloud workloads continue to grow, how can virtualization scale even further without sacrificing performance? Security is another major concern. When many users share the same physical machine, do we ensure strong isolation and prevent one virtual machine from affecting another? Another question is whether we can reduce the need to modify guest operating systems even more, while still keeping the performance benefits that Zen demonstrated. Today, CPUs include built-in support for virtualization. This raises an interesting question about how the balance has changed between paravirtualization and full virtualization. Overall, these papers show that high performance and secure resource sharing can coexist, and it helped shape how we run multiple environments safely on a single machine. Thanks for listening.